please. We'll get this program underway. You're already underway. Everybody's eating. You'll see that. But my name's John Heberger Jr., Vice President. I can try. You'll have to talk with Mike about doing that, though. That's going to be more important. So welcome to the once-a-month lunchtime program of Geologists at Jackson Hole here at the Senior Center. They're very kind to accommodate us, and certainly the food is great and the price is right. So today we have Mike Adler, a member of Geologists at Jackson Hole. Had a long career with General Electric, multiple degrees, more than I think I have fingers for, from MIT. And his son is trying to catch up. Is he going to make it?
He's got 3 and I've got 4, so he's not going to quite make it.
So not bad there at all. So today, Mike is going to talk about some of the very latest things that we've learned about the solar system, all the way out to the very most distant object that man has visited remotely. Nobody was in New Horizons.
I hope not.
It would have been a long, cold, slow ride.
That's right.
So he's going to talk about that today, and I think you're going to see some really, really amazing things. If you haven't followed this on the internet, even if you have, Mike will give a great story. And before I sit down, though, and turn the floor over to Mike, I'd just like to remind everybody that on Tuesday, September 3rd, Bob Tilling, who's sitting right back here with a plaid shirt on the back of his chair, is who is volcanologist emeritus with the United States Geological Survey, who spent a lot of time working on studying Kilauea, is going to talk about Kilauea and that most recent eruption that occurred last year. So that's going to be, I think, most interesting and actually probably quite spectacular. So I'd encourage you to try and be there for that. So, without further ado, now that Mike has got another weapon,
I'm extending my pointer thanks to the vacuum cleaner.
So Mike, the floor is yours.
Wake up and pay attention to it.
Okay, there you go. Okay, yeah, this is a weapon too, so behave. All right, so what we're going to do, this is actually the 4th installment on talks about our solar system. Gavin talks on Mars and Pluto, and then Jupiter and Saturn. And last year I gave a version of the back part of this talk, which I never quite got through. So I'm not sure anyone was here a year ago to see that, but anyway, we're going to see if I can get through it. I have about half the number of slides I usually use, so hopefully I can get through these. Okay, so first thing is we're going to talk about the New Horizons mission. And this is just a little background. It was first launched in 2006, did a spin around Jupiter to pick up some speed, and then it arrived at Pluto, in 2015. And then it was a flyby, and I'm going to give you a review of the Pluto story too, because there's some updates on it. And then it's continued for the last 3 years on to Ultima Thule. And so we're going to first talk about that. This is the actual spacecraft. It's amazing. It's working perfectly. All the instruments are in good shape. Camera, a long-distance camera, and Ralph, which we're going to is the color camera and infrared camera, plus a bunch of other stuff. Okay, so this is the first mission ever. To explore the Kuiper belt, which is the belt beyond, well, it includes Pluto, because Pluto's been demoted, but beyond Neptune. And this is the path that the New Horizons followed out beyond Pluto, and then it picks up Ultima Thule, which it passed, the flyby was January 1st of this year. And so after its encounter, it just continued on 1 billion more miles in 3.5 years to reach it. It's now beyond it. It completed its pass, blasting along at about 14 kilometers a second. It came very close. It came within 3,500 kilometers of Ultima Thule, which is a third of the spacing. It was much closer, 1/3 of the minimum spacing that it had when it went by Pluto. It's a long way away. It's right now it's 4.1 billion miles away. But to put this in perspective, that's 0.0007 light years. Okay.
Wow.
Okay. And the nearest star. Okay, so that's 4 billion miles. The nearest star is 25 billion miles away, and that's 4.3 light years. So, in spite of the fact that this is a long way away, isn't by the global standard or the universal standards, it's really very close. And in fact, when you think about it, the most distant object that man has seen through telescopes is over 13 billion light years away. So this is 0.007 light years. So this is real close stuff. But for us, for mankind, this is as far out as we've gone. So it's pretty impressive. So this is the solar system, mainly focusing on the outer solar system. And here you have Neptune. You can see Pluto here. Pluto has a very irregular orbit, but there's 3 targets that were potentially looked at for the extended mission. And Ultima Thule, which is technically known as, with this nice catchy name here, 2014 MU69. Anyway, it was chosen mainly because it was on the path that Ultima Thule, that New Horizon was on. And okay, so this is it.
So, Mike, is it a moon?
No, it's okay. It is okay. You're exactly in step with what the first bullet on this chart. It's that Ultima Thule is referred to as a CCKBO. Now do you feel like you've been enlightened? Okay, what a CCKBO is a cold classical Kuiper belt object. And so it's not a moon. It is an object orbiting the sun, just like the Earth is orbiting.
So a big ice mass, or
it's more like a comet. So it's partly ice, partly rock, but it's very low density. I'll get into that in a bit. But it's out there where all the comets are formed. The shape is, you can see, it looks like a snowman. The larger lobe here is 13 miles by 12 miles by 4.3 miles, so it's lenticular shape. It's kind of flat, round and then flat. The other one, the smaller one, is more rounded. It's almost 9 miles by 9 miles by 6 miles. Overall, it's 22 miles across. The 2 centers are about almost 10 miles apart. These things are aligned, and the speculation is that they once were separate objects, but coupled together by gravity, and then gradually came together. They're made out of clouds of icy particles. Okay, so here's a little video. If I can get it to start, I should probably do it. Okay, so I want to repeat it a couple of times. You'll see it. You see, this is the first vision. So what the image here has been made. The images are the same size, but what it actually is, and I'll show you another video later. It's actually looking at it from quite a distance. So the first shot, this one, was taken at a distance of 310,000 miles away. And it had an image scale of 1.5 miles per pixel. But then as it gets closer, you'll see that the detail increases. The closest it got in this particular video sequence was 17,000 miles. And then you get to 0.08 miles per pixel, and you'll see a lot more detail. I'll just run it a couple of times, and then you can see it pop into focus. You notice the date here. You see, here's 2018, 12/31. This is close to midnight. 10 o'clock, and there it goes. 2 in the morning, 5 in the morning. Yeah. Okay, so one thing you should notice about it. This is actually the rotation of the object. So it's actually spinning like a propeller. It's not spinning on its axis like this. It's actually spinning like a propeller, and it's only it has the bright side that's here that the spacecraft is looking at is facing the sun. The backside never sees the sun. Okay, take a second. All right, so the surface, this is pretty much the natural color. It has this reddish color to it. It's been measured to have the presence of methanol, water, and other organic molecules. The red color is something called thiolins, which is a reaction of the organics such as methanol with sunlight, and it produces this red dust. Similar stuff is on Pluto and other Kuiper belt objects. This graph here shows the it's a graph that's describing the reflectance of the object, and so its maximum reflectance is 12%. That's called the albedo, which means it's reflecting 12% of the light that it's hitting, and that only occurs in in a few places, like here, here, here. The rest of it is, and you can see it's pretty uniform. It's a little mottled, and you can see that the detail here is not extraordinary, but. Anyway, this all came, by the way, from a recent paper. So a paper came out in May, just of this year. So it's just in time for this talk in Science Magazine. It's quite an extensive paper, about 16 pages of incredible detail about this. If you want a copy of it and look at it, you may. I've kind of synopsized. That's where a lot of this stuff has come from. Okay, so here's some more data that came from that paper. This is it's called the limb topography. But the limb is the outer edge that you're looking at, and so this is how much vertical change there is along the limb. This is Ultima. Yeah, by the way, what they've done is they've described the name for the larger object as Ultima and the lower object is Thule. Now, I didn't say this, it was in the words. What Ultima Thule means is the largest object beyond anything that we've ever seen before. So that's what Thule means. So this is of the larger object. This is the smaller one, and you can see it's about a half a kilometer variation, whereas this is a full kilometer of variation. And let's see, is there anything else I'm missing? I think that's pretty much what's here. Yeah, this is taken by two different cameras. The blue line is taken by the long distance black and white camera, and the red line, which is less detailed, is a color image. But they're pretty much showing the same data. Okay, so this is one of the figures that was in the publicity for this talk. This is what is known as a geomorphological map. And so here's the actual object, and here is the map. And so we'll start with Thule over here. The most predominant feature on Thule, you can see, is this crater. So this is pretty much a crater. It's been named Maryland for whatever reason. It has a couple of bright spots here and here, you can see. And the rest of it is pretty nondescript, but there are these darker veins here, and you can see them in reality here. There also are some crater-like objects up here near the terminator. You can see those here. Those are thought to be, could be craters. Yeah, and the Maryland itself is 7 kilometers in diameter, 2 kilometers in depth from the measurements. Yeah, so we'll go to the next one, and the next one is Ultima. So the larger object. And so if you can see it, there's designations MA, MG. What this shows is there's 7 objects that seem to make up Ultima. They look, and you can see small, they're a little more definition. You can see the borders between them. They're all abutting each other. There's some reasonable relief. You can see that there's these, well, I'm going to get into these craters here on the Terminator in the next slide.
So you think these are chunks that are all smushed together?
Yeah, that's what the third bullet says here. It says the apparent similarity of these chunks is probably a clue to the origin of it. And the thinking is that that's 7 of these chunks came together, glued together, and formed Ultima. So they're subunits of a smaller planetesimals that originally were there. Yeah, and then there's these designations here just relate to, like BM here is bright material, small pit SP, large crater IC, well, that's this one right up here, I see, and pattern material. So they've designated, they're not telling you what it's made out of, but they're telling you sort of what is called geomorphological information about it. Okay, so so here's the sort of the thinking going into this was that there wasn't likely to be seen many real craters on because there's not a lot going on out there in the Kuiper belt. The objects are moving slowly, and so they're thinking they wouldn't see a lot of craters. But there are some indentations, as you can see here, and then of course there's the large. This probably is a crater. They're thinking that these things could be craters, but are more likely things like collapse pits, outgassing pits, sublimation pits, and possibly impact craters. But they're thinking they're more likely to be those things rather than actual impacts. And as a result of that, and this is one of the interesting features of this creature, is that the appearance of this is probably very much like it was 4 billion years ago when it was first came together in the early part of the solar system. The birth of the solar system, which was 4.5 billion years ago. So this looks probably close to what it looked like 4 billion years ago, which is what they estimate it was probably formed. We're looking at a real piece of archaic material here. This is a cartoon that was in one of the references that sort of shows how it probably formed. A bunch of stuff that was slowed down by interaction with the surrounding gas and dust, came together, then gravity pulled it further, coalesced into these two chunks, which ended up spinning around each other, and eventually tidal forces and gravity pulled them together. And the estimate is that that there's no, if you look at the detail of the pictures, there wasn't any signs of fractures or deformations associated with the joining of these two things. So they're thinking it probably came together extremely slowly, like 2 meters a second, or about the speed you actually are walking. So and the other thought is that this is very much like the formation process associated with comets, even though this is not a comet. But comets come from the Kuiper belt. They just happen to have an orbit that circles very close to the sun, and we get the comet effect. But other real comets that we've seen, and we'll talk about one, probably formed much like this.
So, Mike, you think that the two lobes are held together only by gravity?
Yeah, they crunch together at a very end. Well, in fact, I think the next view graph talks about that, the mass and density. Okay. Under these, you guys are hitting this perfectly. They estimate that because of how fast it's spinning, and did I mention that it was 16 times? It goes around. It takes 16 hours for it to go around one loop. So that video I showed you was about a half a loop, 7 hours of it. So it takes 16 hours. And based on that, the fact that it's not flying apart, they're guessing it's about a quarter of the density of water. 0.28 gram per cubic centimeter. And if it was much bigger, if it was like some comets are like a half a gram per centimeter, and if it was rotating faster than 12 hours, it probably would break apart. So they've kind of estimated. They don't have any real way of measuring the mass because there is no satellite. It itself doesn't have its own satellite, but they're estimating it based on what they would expect because of the rotation and having it hang together. The temperature of the object is pretty cold. It's 60 K or minus 213 C on the bright side. And the dark side is probably only 30 K, so it's darn close to absolute zero, what you'd expect for some object so far away. Okay, one last look. This is there's even a little music for this. So this is the one that doesn't magnify the object when it's far away. So you're looking at it as the satellite is approaching the spacecraft is approaching the object. 7 hours, about half a rotation.
So there's no evidence of heat bringing the two parts together, so they're melting
It was thinking
toward
that,
each other?
no, it's thinking that it's a cold fusion, it's cold objects.
So you say it's about a quarter the density of water. What do they think the actual material is?
It's dust and ice, icy dust,
Okay.
which is what comets are made out of.
So,
Yeah.
huh.
And does the probe crash into it after that?
No, the probe is continuing.
Yeah.
It is. It might actually. That's the last view graph of this section of the talk, actually. Oh, we're going to see another video. I didn't want to do that.
Got exit from NASA.
Yeah. Okay. Let's see if I can go to the next view graph.
So are there many more objects in orbit like that?
Yes, a lot of them. It just so. Huh?
Countless?
Countless numbers.
Oh.
This one was selected not because it was selected maybe because of 3 objects. They had a choice because of where the New Horizons was headed, and so they picked this one. For maybe they knew, believe it or not, they had some idea about the shape of this thing ahead of time because Hubble actually imaged this, and they by looking at it in some occultations of it behind stars, they guessed what it was, kind of this shape. And so I guess that interest intrigued them, so they picked this one out of possible 3, 2 other choices. Okay, so what I'm going to do now is, that's all I'm going to talk about as far as Ultima Thule. We're going to talk a little bit about Pluto. Pluto has come back into the news recently, partly because we're pretty sure there's water, a buried ocean on Pluto. And maybe some, so as soon as there's water around, people start speculating whether there could be life. So, okay. Well, anyway, this is, I'm going to show you a few pictures of just general stuff that New Horizons saw when it went by Pluto in 2015. This was taken shortly before the closest, and you can see the layers of a very thin atmosphere around Pluto. Pluto is tipped extremely. It's tipped on its axis by somewhere between 103 and 127 degrees. So it has a very small temperate region, and that's it right here. And even in that temperate region, the temperature on Pluto never gets much above 40 K. So actually, you can see the temperature of Ultima Thule, which is further out, they suggest is actually warmer than Pluto. It's interesting. The axis also tips and turns over its period of 2.8 billion years. The axis is swinging, and it does. Earth has a similar situation, but not that much. And it also takes 280 years to go around the sun, and its orbit, as you can, if you remember, is very irregular. It's not a circular orbit. Ultima Thule had almost a perfectly circular orbit, interestingly, but Pluto doesn't. So that means the temperature on Pluto varied quite a bit over its long history because of the change in the tilt, and also change in just a yearly change because it's changing its distance. So the thinking is the 40 degrees in the 40-degree region. Nitrogen, which is one of the key components of the surface, does flow, and it actually melts at 60 degrees K. But at 40 degrees K, it's enough fluid. Ice doesn't flow at all at those temperatures. But there are indications in these pictures of marks showing things moving. And so it's consistent with the fact that the surface is made up of various ices, one of which is nitrogen. Yeah, the atmospheric pressure on Pluto is, Pluto does have an atmosphere, Ultima Thule does not. Is about, at its maximum, might have been 25% of the Earth's. Okay, so here's a familiar picture. If you've, I'm sure you've all seen pictures like this. This is the famous heart-shaped object. It's called the Tombo Regio. Tombo was the discoverer of Pluto. And it's at a nice toasty 38 K, minus 390 F in Fahrenheit. The color images, which this is, you can see the red color, and the red color is that thiolin that I was talking about earlier when we looked at we're talking about the color of Ultima Thule. But it's the same thing. It's interaction of organics with the sun, ultraviolet in the sun. The Pluto and its moon Charon orbit. They spin on an axis 6.4 days. Pluto and Charon are tidally locked together, and they spin as a unit. They face the same. They face each other, and the part of this part of Pluto is actually directly opposite Charon. We'll talk a little bit more like that. That probably means that this is a heavier. There's more density, more mass in this part, and that's the reason it's locked together. The satellite went by about at the same speed as went by Ultima Thule, 13.7 kilometers per second, about 30,000 miles an hour when it went by in 2015. This picture is a picture of a different side of the planet that was seen poorly because it was going by so fast. It only got a chance to look at one side closely, and the other sides it saw from a much larger distance. This is just a little more detail of that plenum. We'll talk about some of the features of this in a second. This western portion here that looks very smooth was named, for some reason, Sputnik Plantia. And it was first thought to be raised, but it's actually 3 or 4 kilometers depression around over the surrounding areas. And one aspect of the mission was they were able to measure the size of Pluto. So Pluto regained its standing as the largest object in the Kuiper belt. It was thought to be, this other object, Eris, was thought to be somewhat bigger, but it's actually, Pluto has regained the height, the designation as the largest object. The estimate is that it's about 35% ice and 65% rock.
You really ought to say 35% water.
Water, yeah, water.
Can you explain what organic means in that?
Yeah, I'm going to show you what a lot of these ices are organic ices. Okay.
I don't understand that.
Yeah, we'll show you, like methane.
Carbon molecules.
They're all carbon molecules.
Carbon, yeah, frozen carbon like methane. Okay.
CH something.
CH3 is what methane is. Yeah. Okay, so here are some closer pictures of the surface. One of the surprises was the diversity. They didn't expect to see this kind of detail. And this looks a lot like glaciation on Earth. But it's what's actually moving, and there are signs, as I showed earlier, there are signs of things actually moving. And that frozen nitrogen does flow at temperatures of 40 K. These are some of the ice mountains. So these things sticking up through are thought to be water ice, and they named these after Hillary and Norgay. These things are 11,000 feet above the surrounding area.
In all the looks on these, do you see any metals that are larger?
There's no metals visible on the surface.
Most of these are all small atoms.
Everything on the surface of Pluto, as far as anyone has seen, is all ice of one form or another. All the rock and potential metals are all buried in the core of the planet.
So you can't detect them as part of it?
No.
Okay.
They measure, they infer what's going on inside by the mass of it. Okay, so this is another feature of the Sputnik Plantia. If you look more closely, you can see that there are lines. There are polygons, interconnected polygons. They're about 10 to 40 kilometers across, and no craters are visible at all. And these rocks again, they're not rocks, they're ice mountains. Water ice is very rigid at these temperatures. It doesn't flow at all. So what the thinking is that there's actually activity. So Pluto is not a dead planet. There's actual activity going on, and there's upwelling convection of stuff from underneath that was in some form of liquid form coming up to the surface, resurfacing the surface every, at least in this area, every 500,000 to a million years. So that explains why there's no craters in this area, because the surface is always being modified. So this is water ice. Water ice is less dense than nitrogen ice, and so they're floating in the nitrogen.
So the part that you're indicating, if you look at the upper picture where it's located on the actual picture of
Yes,
Pluto,
right there, yeah.
is right at the edge of that heart-shaped business.
Right, exactly.
So
yeah.
that whole thing is being reshaped periodically.
This heart shape, the left-hand part of that heart shape, that what they call the Sputnik plantea, is being reshaped. And I'll get to this in a minute, but the thinking is there's a lake, an ocean underneath that. And that's what you're seeing is actually salty water bubbling up.
Upwelling.
Upwelling, yeah. They call them cryovolcanic activity.
You said that frozen nitrogen melts at 63 below,
Yeah.
but why would it flow at 37 then, which is...
Well, it's because it's things, even solid things have some plasticity associated with them, and so the thinking is, people know this, nitrogen does have some plasticity, so
Okay.
it will move, even though it's in a solid form. Water has the same feature, but not at this temperature.
Sure. Just sort of like the way ice creeps on
Glaciers.
Your roof.
Yes, and on glaciers, the motion, it flows. It flows.
course, that's
yeah,
right.
It flows, yeah.
It's not
Is
63
it the
below,
Sure.
63 above absolute zero.
Yeah, I'm sorry.
Yeah, I'm
right.
sorry, yeah, 60
That's
degrees above absolute zero.
Yeah.
Is the
60.
nitrogen in the form of ammonia?
No, nitrogen, just pure nitrogen. Yeah.
Because liquid ammonia is down in some of these ranges.
Yeah, well, there's probably some ammonia on the planet. Okay, this is to Elizabeth's question. These are various forms of ice frozen material. So this is frozen methane in the yellow. This is some frozen nitrogen, frozen carbon monoxide, and water. And these are people don't understand why that they happen to be in this particular pattern, but the devices on the satellite were able to identify ices of these various materials. One of the other surprises was the variation in color and reflectivity is amazing, and here's a case where the reflectivity of this area is almost 100%, and in this area, which is very dark and red, but only 8%, and they're very close together. It's remarkable that they're that close, and there's so much difference in it. So that was another one of the surprises. Okay. So now we'll move on to this question that. There was a recent article in Astronomy magazine, a little blurb about could life exist on Pluto? So of all things, life all the way out in Pluto. So there's a blog in September in Astronomy magazine if you want to read it. So scientists assess the potential habitability of an environment on three bases. Is there energy? Are there organics? And is there liquid water? So we'll tick those off one at a time. Well, there's pretty clearly organics. They've been measured on the surface, these thiolins, and you can see the frozen. So there's no question that they're organics. There's also a little question that there's some heat. There's radioactive. The rocks in the core of the planet are providing heat for it, and there's evidence of that because of the surface of what you see, the motion that you see on the surface. So there is undoubtedly heat, and at some time, early on, it was probably quite hot during its initial formation. And so organics and heat are present on Pluto. So the question is water. So that leaves water. And so there's several, at least 3 or 4 different indications that there's water on Pluto. One is these cracks. Pluto's surface has got a lot of cracks on it. And one way cracks happen is if you have water and it freezes, it expands and then creates cracks. And so that's one piece of evidence that there could be water underneath. That's either frozen or is in part is being frozen. And we'll get to that in a second. Another piece of evidence is things like this. This is a cryovolcano. It's called Wright Mons, and you can see where it's located here. And that's a cryovolcano, which means that it's actually spewing out frozen, semi-frozen viscous material and spreading it around. And so that's another indication that there was that there's some potential liquid below the surface. The size of this volcano is about 150 kilometers across and about 3 to 4 kilometers high. Central depression of 5 kilometers. So it appears to have disgorged a thick, pasty ice slush in the area. This is a cartoon showing what might actually be the case, what might actually be going on, a surface veneer that we were seeing, frozen water, nitrogen, carbon monoxide, methane, possibly a buried layer, a mantle of low-density water ice, possibly liquid water, and then the hydrated rocky core inside. So, so another feature that one would have expected on a planet that is revolving is an equatorial bulge. There is no equatorial bulge on Pluto. It's almost perfectly round. And the equatorial bulges come because of the rotation, and the Earth has such an equatorial bulge. And one way to eliminate it is if there was an ocean underneath and the top shell collapsed. So that's one piece of thought. Another is it lies, as I mentioned earlier, Pluto and its moon Charon are exactly opposite each other, and they're the same place on both planets' faces, and they rotate as a group, as a unit. So it is very likely that the area in the Sputnik Plantia has higher density, and a higher density could be caused by liquid water. So 3 lines of evidence that suggest a subsurface ocean might be present. The surface fractures, cryovolcanoes, absence of a fossil equatorial bulge, and the fact that there's probably a mass excess in that one area. Now, and as the articles state, this isn't conclusive proof by any means, but it just suggests that it's plausible. So, but one question is, how could an ocean actually survive, a submerged ocean survive out in that part of the solar system? And there's another paper that just came out in June in article, and I referenced it in the paper. When I'll make this available, or if you're interested, you can read it. But what this particular paper posits is that there is a layer of gaseous hydrates made up primarily of a combination of water, H2O, and methane. And the properties of that gaseous layer are that it's extremely insulating, and could have provided a thermal barrier that would keep the water underneath in a liquid form. And they go through a great deal of analysis to show that this is plausible. And when they look at the existence, if this layer didn't exist, this shows the depth, shows going from the center of Pluto out. So this is depth, and this is time. And it shows without such a layer, so this is the ice shell on top, and here's the ocean. It would have frozen quite a while ago. In terms of time from beginning. Whereas if this layer existed, their analysis shows it could have actually protected this ocean and kept it liquid. This is just a graph of the heat flux that would exist in the absence of this layer and in the presence of the layer. So blocking out most of the heat flux from the inside. Okay, so this is the last view graph of this particular section here. So could life exist on Pluto? Well, it has the three things that I ticked off at the beginning. It has the heat, organics, and likely water. So it's interesting to speculate that here we are on the very outer reaches of our solar system, and with a situation where there actually might be there could be some. The conditions for life exist. Whether they're there or not is another thing. But it's pretty incredible to think about that something that far out could actually harbor life.
Can you discuss the radioactive heat source? That implies that there are materials of high atomic number they're radioactive. And is this, what kind of half-life are we talking about? And is the heat flux steady over time? Wouldn't it be dropping?
Well, it is. It's probably similar to what's going on Earth. There's no reason to think it's any different because all of the material in the solar system was formed at the same time.
Oh, that's true.
It may be partly tritiated water,
Okay.
because tritium is generated in fission process.
Okay.
Okay.
So that may be, because you have to have a heat source in order to maintain it. And the thermodynamics back and forth, you have to be able to melt the water in order to be actually liquid phase.
What kind of half-lives are we talking about?
Billions.
Hundreds, thousands, millions?
Billions of years.
Millions,
Yeah.
billions of years half-lives?
Well,
Okay.
tritium is fairly short. I think it's 14 years or something.
Yeah.
But various other
Yeah, I'm sure there's
radioactive.
some other stuff
Yeah, I mean,
that's out there.
yeah. There's no reason to think that there isn't a lot of the same radioactive materials that we have on Earth out there.
Most of them are probably long half-lives, otherwise you'd be
Yeah,
able to
for sure.
detect them a lot easier.
Yeah.
Sure.
Okay, so that's all I'm going to say about the New Horizons mission. And now there's this future. What's the future? Well, the New Horizons spacecraft did not stop at Ultima Thule, and is still going and blasting along at let's see. Well, it says traveling 3 astronomical units per year. I think it's going like 30,000 miles per hour, so it's moving along. The estimate is that its energy sources will exist even into the mid-2030s. So it's possible, and everything is working on it. NASA wakes it up periodically to see. Everything's working on it. Well, in fact, what they're doing, even now, the power from the transmitter on this is in the order of 100 watts or less. So they're accumulating the data. They're still getting data off of it from that pass. So they'll be doing that for another year or more. But it's estimated to live quite a bit longer. So it is possible they will continue the mission. It has fuel. They could continue the mission and proceed to look at, possibly even reach interstellar space, which is what the what are the 2 satellites, the Voyagers, which are both of them now have gone into interstellar space. Okay, so we're going to we're going to talk a little bit about Dawn, something I didn't get to do a year ago. So Dawn is another space mission that is now over. It ended last year, 2018, to investigate 2 of the near asteroids, and it has covered 3.5 billion miles itself. Explored 2 worlds, Vesta and Ceres. These are 2 large asteroids in the asteroid belt. Interesting aspect of the Dawn mission, it was propelled by ion propulsion, and it has some features that are very useful for this particular mission. It's not exactly doesn't produce a lot of power, even though it produces energy. At maximum power, it would take the Dawn system 4 days to accelerate to 0 to 60. So the power output is low, but it has a large energy capability. The one feature of ion propulsion that makes it unique is that it has a very high energy per propellant weight ratio. And so it's up here, and compared to chemical sources of energy, and so it ranks much higher in terms of energy per weight of other sources. If the ion propulsion wasn't used on this, they would need 10 times more propellant, a much larger spacecraft, and a much larger vehicle to do it. So key to this whole mission was the existence of the use of ion propulsion. It was only the second time it was done. This is just a cartoon. There's a propellant supply that in an ionization chamber, and then accelerating electrodes. So the ions are passed through this, accelerated, and then you get a beam of ions, which produce the thrust. Okay, so what the mission was, it launch was 2007. It went by Mars to get a gravity assist, and then arrived at Vesta, the first of the planet's asteroids, in 2011. Departed in September of 12, and then arrived at Ceres in 2015, and it ran out of fuel last November in 2018. So it was around Ceres for 3 years. These two asteroids were chosen for various reasons. One is Vesta is a dwarf, considered a dwarf planet, and well, they both are considered dwarf planets, but they are very different. And one is Vesta is dry, and it resembles rocky bodies in the inner part of the solar system. Ceres has many similarities to the icy moons of the outer solar system. So by studying them both, they were able to think they could put together a picture of what's going on in the inner solar system and the outer solar system. Okay, so here's a picture of, this is what Vesta looks like, and this is what Ceres looks like. And I'll show you much more, a few more pictures. This is a detailed picture of 10,000 images that were taken that show the entire planet of Vesta. It has a diameter of about 330 miles, rotation period of 5.3 hours, orbital period about 3.6 years. It's about 2.4 AU, meaning 1 AU is the distance that Earth is from the Sun, so it's 2.4 times further out, from the Sun than the Earth is. Unlike a lot of asteroids, Vesta is differentiated, which means it has a different layer. It has different layers in it. So it has a crust covering a rocky mantle made of likely iron and nickel. So it's considered a protoplanet. That has a very prominent feature on it, and it's Rheasilvia. It's a crater that is incredibly deep. It's 19 kilometers deep, and a central peak that rises 23 kilometers. So it comes very close to being the highest relief in the solar system on this one asteroid. It's estimated that the impact occurred about 1 billion years ago and excavated about 1% of the volume of the asteroid, and the material that was extracted from that or blown out accounts for a lot of the smaller asteroids in the asteroid belt. So a whole class of near-Earth asteroids came from Vesta, and as a result of an immense collision on it. So this is Ceres. Ceres is larger. It's the largest of the asteroids. It's not as large as Pluto. It's 2.6 times smaller. Has a diameter of almost 600 miles. It's the only object in the asteroid belt that is actually rounded by gravity. Gravity eventually crunches things together, and eventually large objects will all end up being circular, give or take an equatorial bulge. It has a period of 4.6 years, and it's a little further out, it's 2.75 AU out from the Sun, and it rotates every 9 hours. This is a cartoon showing it has it's thought to have a density that is quite a bit lower. It's way higher than the Ultima Thule, but 2.5 grams per cubic centimeter compared to like Mars, which is 4. So it's not nearly as dense as Mars is. It is differentiated. It does have various layers. The mantle is thought to be hydrated rocks like clays and ice. External layer of about, and this is the mantle, the external layer about 40 kilometers, various materials, ice and hydrated rocks. And then inside is, inside is area of hydrated rocks. I screwed up. Inside is hydrated rocks. The outer, and then this area here may be a layer that contains, might be liquid rich. In fact, based on the mass of it, the thinking is that it might be 25% water. And if that's the case, it would actually have more water than Earth. So this is one of the, there's a lot of craters on it, but there's none large one, there are very few large ones, which is a little bit of a surprise, thinking that there's some activity smoothing things out. But there is this one large one here, and it's about 175 miles across. This particular, it's called the Okator crater, and the bright spots have been actually observed by satellites from the Earth. And the thinking is, from the satellite, Dawn figured out that it was mostly sodium carbonate, so implying some kind of hydrothermal cryovolcanic activity on this planet as well, on this object as well. Then the very center of it is kind of interesting. It's a mosaic, so this is a picture taken from an altitude of only 34 kilometers. That's pretty amazing. Look at the detail in that picture. That's something. So, this is the sidewall, an image of the sidewall of the Dawn spacecraft. So it was getting down there. This is 33 kilometers above the planet, so it is close. I mean, it's 20 miles maybe. It's skimming. What happened as the mission was getting ready to end, NASA brought the satellite in much closer to the planet, and so a lot of those pictures were taken. This is the only mountain on it. It's got a name of Ahuna Mons, and it's about 5 kilometers high. And the origin is unclear. It might be a result of some cryovolcanic activity. And there's interesting that this next picture, this is an object on the Earth that has a similar shape. And this is up in the Canadian Arctic. I just ran across this today, actually. They're called pingos. And they're thought to occur because of material punching up through different sequence of freezing thaw events, and material coming up from the interior during that sequence. So that gives one clue as to what actually may have caused that mountain on Ceres. And these are just some very neat pictures of that were taken of the planet. You can see it's very irregular on the surface. Okay.
So did it crash on Ceres?
That I was trying to find that out. They lost contact with it because they ran out of fuel.
Okay.
It ran out of fuel, and so without the fuel, they can't orient it so that the antennas are pointing in the right direction.
Yeah.
So they don't know. They actually don't know, but eventually it will.
Are they keeping listening with the hope that it
might eventually.
pass?
I don't know. I knew that someone would ask that question, and I.
Okay.
And let's see.
We would assume it probably would crash.
Yeah, I would assume eventually it will crash. Almost certain.
Yeah.
Maybe not, there's no atmosphere.
Okay, so this is a video that NASA put together, and it's kind of neat.
Ooh.
Yeah, when you say no atmosphere, there's probably something out there. Okay, so this is a flyover you'll see now of the planet over the brightest area. So there's that Okator crater.
How deep did you say that was?
It was very deep. I'll have to go back and remind myself. All right, so that's that. Let me see, just go back. It was, let's see, 175 miles in diameter. No, that was the maximum. They made 4 kilometers deep, 60 miles wide crater, 4 kilometers deep. Okay, so the last part of this talk is the Rosetta mission. I only have a few view graphs here, or slides. The Rosetta mission was launched by the European Space Agency to actually go visit a comet. And it actually reached the comet in May of 2014, and this is a picture of the comet that was taken. And you can see, look at the shape of this and think about it relative to in Ultima Thule. It looks a lot very similar. And it came from the same place, the Kuiper belt. It's just that Ultima Thule is staying in the Kuiper belt. Comets don't. They have this very irregular orbit. So its mission, it actually orbited the comet for 17 months. And as you probably remember, it did have a rover that, or a object they tried to get onto the planet, and it bounced and ended up in a crack. So right in the middle of where the two objects joined together. But this is it's pretty incredible. The mission. It was launched in 2014, and it went Earth flyby, Mars flyby, second Earth flyby to gain speed, and then it so that was 4. Then asteroid flyby 5 is increasing 6 and 7, and then eventually it's catching up to the comet, and the Philae, which is the lander, lands on the comet in November 2014, and the mission ends in 2015 in December. So this is an image that was taken from only 28 kilometers above the comet. The density of the comet is thought to be about 60% of water. The body is 2.5 by 2.1 by 1 miles. And the head spans 1.4 by 1.6 by 1.1 miles. So this is a picture of the surface of it. Look at the detail in that picture. It's just incredible. Has a resolution of 1.7 meters per pixel. And the actual distance is 3 kilometers by 1.7 kilometers, 3 kilometers by 1.7. So this is the lander. This is what the the satellite looked like, and this is the lander, the Philae lander. One of the things that was done, what they did determine, is they looked at the ratio of deuterium to hydrogen, and it was found to be 3 times that are found on Earth, 3 times on terrestrial Earth water, which suggests strongly that comets of this type were not the source of water on Earth. There's always this question of where did the water come from, and one possibility is comets that collided with Earth, but with a deuterium to hydrogen ratio that high, it is not likely. But that's a potential future talk, is where is the water in the solar system come from. Here is the lander. The lander was not able to complete its mission because it bounced. This is very low gravity, and it hit and it bounced up and it ended up in this crack. And it lost contact with the sun, and so its batteries died. But it was able to make measurements of a lot of materials, various organics detected. But just landing, when you think about it, here's this comet moving at 84,000 miles per hour. and to have a satellite first get, reach it, orbit it, and then actually put something on the surface of it is pretty darn amazing. So, and I think this is the last picture. Yeah, September. Okay, so that's the end of the formal talk. So I'm showing here a couple of pictures I took. Now, did I take this picture? No. But what this is a picture of the south pole of Jupiter, and it's taken by something called the Juno cam, which is the camera that's mounted on the Juno satellite, and it was taken from the Juno satellite orbits. Unlike all the other missions to Jupiter, it orbits over the poles. It orbits over the poles. And so it gets very close to the planet at the equator, and so its pictures are very close up at the equator, but when it gets over the poles, it's up a way, so you're actually seeing pretty much the whole planet. It's up about 100,000 kilometers over the South Pole. So this is a combination, but because of the limited field of view, there's actually 3 separate pictures were taken. So one of the unique aspects of the Juno mission is they made the raw images available to the public, to amateurs like me. And so I took their 3 of their raw pictures from the first, third, and fourth orbit. So it wasn't real easy, but I managed to put them together pretty well, and I compared it to some others I've seen online, and I think I've done as well, if not better, than most of them that I've seen. It's hard because things are changing between those orbits. These orbits are 33 days apart, and these things aren't exactly the same, and so matching things up and at the boundaries was difficult. But it's pretty incredible. These cyclones these are views that before Juno no one had ever seen, because no one had ever seen the poles. All you see are the bands, are the traditional bands. But these cyclones are about the size of the Earth. Okay, here's another one. You'll recognize this. This is taken from the 18th orbit, and it gives you a real close-up of the red spot. Two of the raw images were combined. This was taken from -40 degrees, so it's in the southern latitudes, from about 27,000 kilometers. And the red spot is about 3 Earth diameters. And the last picture is one that is fairly close up. It's taken from the 20th, a very recent one that was just taken within the last year, and it was taken at 39 degrees north and about 10,000 kilometers. And this is combining two images, but you can see these incredible. Before this Juno has gotten these images from the Juno satellite have the most detail of any images that have ever been seen of Jupiter, because it's so close. So that's it.
Wow. Thank you, Mike.
Further questions?
Questions from Mike?
Yeah, you've been asking questions all along, which is fine. But any further?
I heard you used the word planet when you were talking about Pluto.
No, yeah, right. That's a slip. Well, yeah, or I'm just showing my age or something.
But you called it a subplanet or a dwarf planet?
Dwarf planet is what they call it. Yeah,
There still are.
So there's a little bit of status to it.
Yes, yeah, and Ceres is considered a dwarf planet too. Yeah. Yes.
And I understand you to say, kind of in passing, that whatever there is out there occurred at the same time.
Pretty much in the solar system, things happened. The evolution of the solar system occurred about 4.5 billion years ago, and the sun formed at that time, where you had gravity finally pulling together enough hydrogen together to get up to 15 million degrees Kelvin. That would cause a nuclear reaction to occur. And then all the other debris that was around. You see, the sun, all the stars are formed from debris, dust and various gases, particularly hydrogen. But And the sun, our solar system is thought to be a third generation. Our sun in our solar system are thought to be third generation. What does that mean? First generation stars had only hydrogen and helium in them and a little lithium, because that was the primordial elements from the Big Bang. Once the first generation stars died, they used up their fuel. Some of them supernovaed. And in the process of supernova, well, the stars themselves generate the heavier elements. The astronomers call them metals. So they generate the heavier elements. And a star that goes supernova, a star that's 10 times the size of the sun, goes to a supernova, it will generate elements in the first 15 minutes of its supernova, go all the way out to uranium, the very heaviest elements. And so we obviously have uranium, we have all these heavy elements. And so the thinking is 2 sets of supernova explosion generations of stars occurred and created a dust. And if you look in some of my pictures, but pictures of our solar system, or of our galaxy, you'll see clouds of nebula, clouds of gas and dust, and then like the Orion Nebula. And inside these clouds of gas and dust, stars are being formed, where the material that's is being gravitationally compacted, and eventually it gets heated up, and if it gets heated up enough, a star gets formed. But there's stuff left over from in the cloud that formed it, and the objects that were really close to the sun, like the terrestrial planets and some of the asteroids, they are formed. They are called the terrestrial planets, and they're solid. They're rock. Whereas the outer planets were formed from the material out there, which was largely gaseous, and they are like Jupiter and Saturn, and exception being the Kuiper objects, which are rock-like, ice-like, but Pluto. So I don't know if I'm answering your question, but I'm just telling you that the whole process that formed our solar system was an event that started with forming the sun, and then the various planets eventually over periods of millions, hundreds of millions of years coalesced.
Thank you.
Yeah. And there's a lot to all of this. People have pretty much figured that Jupiter made a pass into the inner part of our solar system at one point and cleared out a lot of the stuff, and then ended up settling, because the planets interact with each other, and so the final set of orbits that we now see are the result of a lot of chaos that occurred in the early part of the formation of our solar system.
Thank you.
Yeah.
There's an odd shape correlation between the heart-shaped piece on Pluto, and you said the dumbbell-shaped item is right across from it?
No.
Charon, the moon.
The Charon, the moon, is
okay.
the Pluto's moon is right across from it, and the same side of the Charon and Pluto are facing each other, and they.
Didn't you say though? I know I remember hearing that, but that they were facing each other. But earlier, I thought you said that the little dumbbell thing also faced Pluto.
No.
Okay.
Yes, you're talking about.
Faces the sun.
Yeah, you're talking about Ultima Thule. Yeah. No, that's of course.
Further away.
That's a whole billion miles further out from Pluto. But it is an interesting shape though, and it's a propeller. It doesn't rotate along its natural axis. It rotates perpendicular to its natural axis.
Hey, Mike?
Yeah.
In a lot of the slides showing the interiors or the estimated interiors of these bodies, talks about a rocky core or a rocky layer. Can you get any more specific in there from the computations or modeling of the mass to get a better idea of what is rock? Because we know on Earth, rocks can range widely in composition.
Yeah. Well, the answer is from these kind of single flyby missions, they can't learn an awful lot. They can't learn an awful lot. But on a mission like Juno, which is going around there, they are learning a lot more about Jupiter, because they are, for the first time, using microwaves, they are penetrating much further into Jupiter than they ever have before. So they're learning more about, they're now thinking that Jupiter may not actually have a core, may not have a solid core. At one time they thought it would, but now the latest thinking is it probably doesn't. But it's all inference based on measurements the upper couple hundred kilometers of the
It's
surface.
all averaged out.
Then they do a lot of numerical modeling to try to infer what is probably, also knowing the pressures, because in Jupiter, a great portion of it is metallic hydrogen. And it's the metallic, and the magnetic fields on Jupiter are not caused by a rotation of a dynamo in the middle. It's caused by rotation of this metallic hydrogen nearer the surface, producing magnetic fields 1,000 times higher than on Earth. Huge fields. That's why this Juno satellite is, they're not sure how long it's going to last. Whether its goal is to make 35 of these per Hovis. It's now 20, or 33, so it's mostly way through it. But it's going through, it's getting real close to the planet, within 3,000 miles of it at the equator. So it's going through some incredible heavy radiation. Somehow, and the other question about the cameras, people were wondering whether the camera would stay working, being subjected to these huge magnetic fields and radiation. But at least for 20 of its orbits, it's survived.
All right, thank you.
Thank you.
Thank you.